Okay, welcome everyone to the next Young Research Seminar. Today we'll have a talk from Christiane Klein from the University of Leipzig. So the general interest of Christiane is generally high energy physics, and in particular the mathematical foundation of quantum field theory. And she does a PhD on quantum field theories in deuterium black holes in the context of strong cosmic censorship conjecture. And that's also where she will give a talk about today. So without further ado, the floor is yours, Christiane.
Yeah, thanks very much for this kind introduction and for this opportunity to speak here today. As some of you might be able to tell from my voice, I'm a bit sick, but I hope I get through this talk somehow. So the topic I want to speak about today is actually a bit broader than what I'm particularly doing, because I want to give you a little bit of an insight into quantum field theory in curved spacetime and the algebraic approach to quantum field theory, and why this might be something that, even though you might be doing some completely different ansatz to quantum gravity, is still something you might be interested for and might look out for when there are papers on the archive. Okay, so let me give you a brief outline of my talk. I have divided my talk up into 4 parts. In the 4 parts, in the first part, I will try to give you a motivation why this talk should be interesting to you, and why, when we're talking about quantum field theory in curved spacetime, it makes sense to use the algebraic approach, and also give you a very, very brief introduction to the just guiding principles of this approach. And the next 3 parts will actually focus on a specific example, namely the theory of free scalar fields, which in flat spacetime is not that interesting, but in curved spacetimes it can actually become quite interesting. And in particular, I will show you one example of how in this particular example we can construct the algebra of observables. I will then tell you a little bit what the Hadamard states that a lot of people in this algebraic quantum field theory fields talk about are and why they are so important. And then in the final part, I will tell a little bit about my ongoing project, how it is very difficult in this framework sometimes to construct a state for a certain purpose on a certain spacetime. Okay, so without further ado, let's get into why should you, as a quantum gravity researcher, be interested in algebraic quantum field theory? Okay, let me start a little bit simpler. Why should you be interested in quantum field theory on curved spacetimes? Well, I would argue as follows. So far, at least to my knowledge, there is no complete theory of quantum gravity, but there are certainly some promising candidates. So at some point, we will need to test the theories. Ideally, we would do so on experimental data, for example, by comparing black hole shadows with what we actually predictions for black hole shadows with pictures of black holes. But so far, experimental data is kind of sparse. So another approach one could make is be like conservative and say, okay, let's compare with results from well-established theories in some, for example, more low energy regimes, and see if our theory can reproduce this. And one such regime would, for example, be the one where quantum effects of gravity are still negligible, so our curvature is well below the Planck scale, but the quantum effects of matter are not. And this is exactly the realm of quantum field theory on curved spacetime. And in this realm, we could then hope to describe matter and gravity by the semi-classical Einstein equation, where on the left-hand side, you have completely classical gravity, and on the right-hand side, you have the expectation value of the stress energy of your quantum matter. Now, this equation in itself has a lot of conceptual problems and is very difficult to really solve, and I won't get too deep into that. There are other experts on that than me. We will take it more as a motivation. When we define our quantum field theory on curved spacetime, we will keep in the back of our minds that we want to have observables defined in such a way that they're at least compatible with such an equation, in the sense that, for example, the stress energy tensor should be conserved and that it should be a covariant tensor also under the change of spacetimes. Okay. Now, you might say, well, that sounds like a nice regime, but is there anything interesting to observe there? And I would say, yes, there is. This is a very short, very incomplete, and very biased list of some results that you can get with the help of quantum field theory in curved spacetime. The first I want to mention is the Unruh effect, which basically tells you that a uniformly accelerated observer, even in flat Minkowski space, will feel himself immersed in a thermal bath of particles, even if the quantum field is in the Minkowski vacuum state. And this is one of the first cases that you come across when you study QFT in curved spacetimes, where you notice that the concept of particles is not really that well defined anymore if you go away from flat spacetimes. The second effect I want to mention is probably the most famous one, which is Hawking radiation, telling you that black holes formed from the collapse of some body should radiate particles as though there were black bodies of a temperature which is proportional to their surface gravities. And another topic that has a lot of research going into it, of course, is quantum field theory on cosmological spacetimes. And here I have highlighted only two aspects of it. First of all, of course, the quantum fluctuations of the inflaton field and also the scalar part of the metric during inflation can be modeled by quantum field theory in curved spacetime. And you can also try to model cosmological expansions beyond a certain threshold by considering all the fields as essentially quantum fields, and then really from that trying to derive the typical FLRW spacetimes that we have in the under CDM model. And then I want to highlight also two things that I've worked on so far in my PhD. As Linda already mentioned, one is quantum fields inside black holes, in particular in connection to the strong cosmic censorship conjecture. So the strong cosmic censorship conjecture is basically the idea that the inner horizon at which determinism of a black hole, at which determinism breaks down in the sense that if you go beyond that, then what happens beyond that is no longer determined by initial data, really becomes a singularity, because any perturbations of the empty space initial data will accumulate there so strongly that they basically force this horizon to become a singularity. And what my supervisor, Professor Holland, showed on this paper together with Robert Wald and Dr. Zahn was that even if classical perturbation don't form a strong enough singularity to make this conjecture hold, then the quantum perturbations will become so strong near this horizon that in fact they restore this strong cosmic censorship conjecture, even independently of the state that your quantum matter is in initially. And my contribution to that here was basically some numerical backup for this claim. And the group of Zilberman et al. Has also done a lot of computations of quantum field expectation values inside black holes in similar scenarios.
Sorry, Christiane, there's a question in the chat.
Yes, please.
So first of all, the people, if you have a question, feel free to just unmute yourself and speak up. The question in the chat is that in what kind of black holes?
Oh, my particular work was Reisner Kerr-de Sitter black holes. So charged black holes in the presence of a cosmological constant. For other black holes, particularly, I think most black holes without the presence of cosmological constant, it has been shown that the strong cosmic censorship conjecture, at least in some sense, holds. But yeah, this highly charged black holes in the presence of no cosmological constant was the case where it could still be broken classically. and where we could show that even if it's broken classically, then quantum effects will restore it. Yeah, thanks for the question. Yeah, and the last point I wanted to add here is my last work, which was, well, as I just mentioned, we looked at charged black holes, so it makes sense to also look at charged quantum fields. And if you have charged quantum fields, you would expect that they also induce a charge current so that they transport charges throughout the black hole. And we have computed this charge current near the inner horizon. And this is the result here on the left, which was very surprising to us because what we would naively expect from the particle picture, again, is that the black hole would be discharged by just pair creation and then the charged particles being accelerated in opposite directions and just discharging the black hole. But it turns out that apparently there is some parameter regime where in fact the quantum effects can enhance the charge of the black hole. So again, this is a very nice example of this naive particle picture really breaking down in curved spacetimes. Okay, so I would say that there is a lot of interesting effects that one can study with quantum field theory in curved spacetime. One can try to maybe duplicate with your favorite theory of quantum gravity. Okay, so hopefully I have now convinced you that quantum field theory in curved spacetime is something interesting to look at. Then you might still ask, well, why do I need the algebraic approach to quantum field theory? Well, usually if you have your first quantum field theory class, then you learn that you have a Hilbert space, which then in quantum field theory is a Fock space, and your states are just raised in that Hilbert space, or their density matrices, and your observables are operators on the Hilbert space, or maybe if you're a little more advanced class, you talk about them as operator valued distributions. But the point is that if your classical configuration space already has infinite dimensions, which is the case in quantum field theory, then there's actually not a unique Hilbert space. There are a number of unitarily inequivalent Hilbert spaces that you can choose upon quantization, second quantization. This is not a problem in flat spacetime because basically Poincare invariance gives us a unique Poincare invariant vacuum state, which then allows us to choose the one Hilbert space which has this Poincare invariant vacuum state as its ground state as our Hilbert space. However, if we're considering a general space-time, there might be no Poincare invariance or even no symmetry at all. So we don't have a unique ground state anymore. We might not even have anything that deserves the name ground state. So we don't know which of these unitarily inequivalent Hilbert spaces we should choose. Sure, we could make a choice, but the thing is we might miss physically relevant states, physically interesting facts by making that choice a priori. And this is why people like the algebraic approach, because the algebraic approach basically puts choosing the Hilbert space last. And how do they do this? Well, the basic idea of the algebraic approach is not take the Hilbert space as the fundamental object you then build things upon, but start with the observables and their algebraic relations. So how you can multiply and add them. And this abstract algebraic structure of the observables as your fundamental object. And one kind of abstract way to then view what a quantum field theory does is that it basically maps from spacetimes, globally hyperbolic being the condition that it has so-called that spacetime should have so-called Cauchy surfaces, so surfaces that are crossed exactly once by every time-like geodesic, which basically allows you to give initial data on the surfaces. So it maps these spacetimes to algebras of observables. Now I put the C in brackets here because you don't necessarily have to to take so-called C-star algebras. It can also be different kinds of algebras. But important is that this mapping is done in such a way that it also maps nice isometric embeddings between spacetimes to corresponding maps between algebras. So in a mathematical sense, it is a functor between the category of these globally hyperbolic spacetimes with nice isometric embeddings as their maps and these spacetimes as their objects to some category of algebras which have the algebras as their objects and these unit preserving star homomorphism as their maps. And by nice, I'm
sorry, there's
yes.
another question in the chat.
Yes, please.
So the question is, does not a symmetry usually mean that you can have a degenerate vacua?
So hi, Christian. Can you hear me, Christian?
Hi.
It's me.
Yes.
Yeah, hey.
Hey.
So I'm just confused by the statement you had in your previous slide. I mean, maybe
Yes.
I'm misreading it, but you
Yes.
say something like no symmetry gives no unique vacua or something, but should it not be that if you have a symmetry, you can have degenerate vacua?
With no symmetry, I in this case mean no spacetime symmetries. And the way the ground state or vacuum is normally defined in quantum field theory on curved spacetimes, because that's really not super trivial once you get out of flat space, is that basically it's defined with respect to a time-like shift.
Can you go back? Can you go back to that slide? Sorry, can you go back to the
sure.
slide so I can maybe see if I can catch on?
I don't know if I can. No, I can't. Okay, I can. Yeah.
Weird. Okay, there we go. Yeah. Okay. So please keep talking. Yeah.
Yeah. So basically, the idea is well, how you naively define the ground state in flat spacetime is basically the state of lowest energy, right?
Yeah.
Okay. So what is energy? Energy is basically how you evolve your state in time. But if time is non-unique because you're in a curved spacetime, how do you define this time? You can take any time coordinate. Well, you can say, okay, I take the time-like killing field that my spacetime have, but what it doesn't have any. You know what I mean?
Yeah, sure. But okay, so you no longer define it by like the minimum of your potential or something like this. This is no longer possible?
Yes, that becomes really non-trivial if you go to curved spacetimes. Okay.
All right, well, then that makes sense. Perfect, thank you.
You're welcome. I think there was some raised hand.
Yeah, hi. I would just like to ask whether there is a general recipe in the algebraic approach towards the problem of quantizing zero modes when I have, for example, master scalar field on some non-trivial topology. Does the algebraic approach provide an answer to that?
Unfortunately, I'm not sure, honestly.
Okay. Yeah, sure. No worries.
Maybe there's some other AQFT people in the audience who can answer this question, but.
So just to clarify, do you mean like the massless theories on two-dimensional spacetimes, or?
Yeah, on 2D, I think there was recently some proposal on using, I think, time machines, but also in more general, maybe if there is some, because I know that is a problem in ordinary QFT and curved spacetimes, but yeah, I was wondering whether approaching it algebraically, maybe there's a more established way to do that. But maybe we can also discuss this later. Thanks.
Yeah, no problem. Let me also think about this for a second, maybe in my head while I continue. Okay, so yeah, I think we were here. Okay. So yeah, so mathematically speaking, it is a functor. And then we also would like our quantum field theory, of course, to be causal. So we demand that if two spacetimes can both be embedded into a larger spacetime with such a nice isometric embedding, such that their images are space-like separated, then the images of their algebras should commute. And finally, we will also demand in this particular example the time slice axiom, which says that if the image of one spacetime in another already contains the Cauchy surface of the spacetime n, so basically a surface of initial data, then the image of the algebra is already the complete algebra. So in a sense, we can again determine everything from initial data. And so this is like the first half of the algebraic approach, a very rough idea of it. Now the second half is how do we get back to states and Hilbert spaces? Well, states, the very basic definition in this algebraic approach is quite simple. We define them as linear maps mapping from your algebra to complex numbers, such that they are positive and normalized. So the star is an operation on your algebra, and you can think of it basically as conjugation in the Hilbert space sense. It works also in the same way, so and will become that once we go to Hilbert space representations. And we will see that we will have to restrict that later a little bit, but you can basically think about these states now as really taking expectation values of the observables. And one nice thing is that now, after we have for abstract algebra, for which has been constructed in a way that is consistent with also changing spacetimes, so basically in a consistent way over all possible spacetimes, and we have chosen a state, we can then go back to the Hilbert space by the so-called GNS reconstruction theorem, which tells us that once we've chosen a particular state, we can construct a unique Hilbert space and representation of algebra on a dense subset of that Hilbert space, because our algebra need not be bound operators unless we're in the C star case. And also a vector in that Hilbert space, such that our state now really becomes just taking expectation values, if you want, in the usual way, by just taking the representation of our element of the algebra and then sandwiching it between the brackets of this vector in the Hilbert space. So what the algebraic approach really has given us is that we can study this abstract algebra and really do the step of going to choosing a state and choosing a Hilbert space last, so that we don't miss out on anything important. Okay. So this was my very, very brief motivation and rundown of the algebraic approach. And I will next restrict to the example of free scalar field theory. So if there are any more questions up to this point, that would maybe be a good time.
So maybe I have a question. So as far as I understand, or I'm wondering a bit, so even though you now at the end choose a Hilbert space, can you not somehow identify, so can you not roll this up the other way around and now say which Hilbert space, so you fix some algebra and maybe you want to look at one specific operator, but can you then not somehow say which Hilbert space is that if you would immediately construct Hilbert spaces at the beginning? You know that so you said now you went like the other way around of saying not I choose a Hilbert space and I look at operators on that Hilbert space, or rather you choose some algebra of operators and then construct a Hilbert space to that. But can't you somehow make a connection between these two? So rolling it up backwards in a sense?
The point is really that the algebras can be constructed in a way that is really consistent throughout different spacetimes, and that really basically is consistent throughout this whole, that really encompasses all the, we will see later that really encompassing all the observables in your field theory is a whole different story on its own. But if you will see that once we go to curved spacetime, states really, in a sense, become a bit problematic, because while the algebras are perfectly local, so they can be really local, observables can be localized, states will inherently depend on the global properties of your spacetime.
Okay, I see. Okay, yeah, maybe this will become clearer for me later. I will maybe come back to this point. Thanks.
You're welcome. Okay. Well, so maybe this will also become clear in the next bit, where I talk about one example of how we can construct an algebra. So as I said, I want to talk about the example of free scalar field theory. And so let me state a few facts, or the most important facts that I really need for my construction. So we will talk about a real scalar field satisfying a Klein-Gordon equation of motion. So I will denote with this curly K the Klein-Gordon operator on any given spacetime. So this box G is just the wave operator on the given spacetime, and M squared is the mass term. You could also add like a non-minimal coupling to the Ricci scalar, and probably also some potential terms here. I will stick to the mass term for now, but adding potentials or non-minimal coupling doesn't really change much of the subsequent construction. Okay, Sean is just spamming the chat. One result one can then prove basically about this equation, if you will, is that if you have a globally hyperbolic spacetime, then there will be unique, retarded, and advanced fundamental solutions to the Klein-Gordon equations. So basically inverse operators to the Klein-Gordon operator, which have the property that the support of E plus minus acting on phi is contained in only in the future or the past of the support of phi. And out of these two, one can then build a so-called commutative function, which also has a bunch of other names. I will call it the commutative functions, which is just the difference of the two. And this commutative function then maps compactly supported smooth functions on a manifolds to solutions of the Klein-Gordon equation, which also have the property that their Cauchy data is compact, meaning that if we restrict E acting on phi to any Cauchy surface, then the support of this restriction will be compact. One can also view this as a y distribution or a bilinear map on compactly supported functions, namely by just integrating one of them against E acting on the other over the whole manifold. And one can show by using Stone's theorem and the fact that E of H solve the Klein-Gordon equation, that this is the same as integrating this current here, or the normal component of this current here, over any Cauchy surface sigma over spacetime, any space-like Cauchy surface. And this, in particular, this is independent of which Cauchy surface you choose. And two facts, this E of F and H is antisymmetric, which is probably most easily seen here. And it vanishes if the supports of F and H are space-like separated. Okay, so this is basically our classical data. So now we want to build the algebra. And one way to do this is going with the so-called CCR, or canonical commutation relations algebra. So we take our algebra to be the free unital star algebra generated by the unit element, which we call 1, and abstract elements, which we call phi, and which are labeled by compactly supported smooth functions, or we will say also say test functions. And we will identify two elements of the algebra if they satisfy one of the following four relations. First of all, these abstract objects phi should be linear in their label. They should be permission. So if we act with our star operation on it, that should just be phi labeled with the complex conjugate of f. We have a commutation relation. So phi of f and phi of h. Commutator is just I times the commutator function of f and h times the unit element of our algebra. And they also weakly satisfy the equation of motion, meaning that the phi is labeled by the Klein-Gordon operator acting on some compactly supported function, then this is just 0. So in a sense, you can think of these abstract elements phi as being our quantum fields smeared with some test function f. And we will also specify how we go from one spacetime to another. So if we have some nice isometric embedding of m into n, then the image of phi of f, where phi is on m spacetime, is the phi on the n spacetime labeled with f after the inverse of sign. And one can indeed show that this satisfies all the requirements that we've put on basically quantum field theory and forms an algebra. Okay. And what do elements of this algebra now look like? So they're basically of the form up here. So they are finite sums of finite products of these phi's. So finite sums of finite products. What they explicitly do not contain are things like the smeared stress energy tensor, where we would like to first square phi and then smear with the test function and probably take some derivatives. This is not something that is yet in our algebra. So while we have constructed an algebra that somehow describes the observable of this free scalar field theory, it does not yet contain the stress energy tensor, which is very much an observable we're interested in. So to also encompass that, we will need to extend our algebra. And what we need for that is basically a notion of normal ordering. In flat spacetime, as you might know, you usually normal order things with respect to the Minkowski vacuum state. Well, that is not an option, as I mentioned, because we might not have a unique vacuum state. And even if we chose a state, there is, I think it even has been shown that there is no general way to consistently assign a specific state to each spacetime like we've done with the algebras. So we cannot choose states to do the normal ordering. Instead, what one does to get this normal ordering in a local and covariant way is to define it with respect to the so-called Hadamard parametrics. And then we can restrict ourselves to so-called Hadamard states, which then are states where such expressions like the stress energy tensor are in fact well defined and have finite expectation values. And this is why these are then considered as the physical states, because there we can actually assign them basically finite energy densities.
Sorry, can I ask again something? So,
Sure.
So why is the stress tensor not in AM? So first of all, the first line says like linear in the fields, but so for me this looks like it's non-linear in the fields. Like you build some.
It's linear in the fields, right? In the sense that you first smear the field. So you basically smear every field separately. So what you explicitly don't do is like take coinciding points limits of two fields and then smear this coinciding point limit, which is exactly what you would like to do for the stress energy tensor. So here, for the stress energy tensor, you really would like to evaluate two fields at the same point.
I see.
And then
okay,
sure,
okay.
maybe you can smear out where that exact point is, but you still would like these two fields to be at the exact same point. While here, technically, every field is smeared separately, so they're not at the same point.
Okay, and by the construction somehow, can I somehow see that it is not possible to to evaluate? So in my language, to evaluate the fields at the same point, or why is this not possible? So why is this not contained in the algebra? Is it simply like how it's constructed, or why?
Yeah, basically because how it's constructed. In the way that I've constructed it here in this example is because the elements of our algebra are basically these already smeared fields.
Mm-hmm.
And if we multiply them, we just get products of smeared fields, but they're all
I see. Okay.
smeared before we multiply them. So they will never be like exactly at the same point.
Okay, okay, thanks.
You're welcome. I hope this maybe also makes the previous question a bit clearer. Okay.
Yeah.
Okay, great. So yeah, now I've said, well, we normal order with respect to the Hadamard parametrics and then restrict to Hadamard states. So I guess the natural next question would be, what are these Hadamard states? You might have, my first experience was just coming across this name like multiple and multiple times and really sitting there like, but what are they? Okay, so let's address this question. So before going into this, I will restrict to actually a different class of states, which are the so-called quasi-free states. This is purely a convenience. These states are states that are completely determined by the behavior of their two-point function. So the expectation value of two smeared fields multiplied with each other, which we can also consider as being a bidistribution. So a distribution of two compactly supported functions. And when restricting to this class of states, the basic idea is actually quite simple. So a quasi-free state is Hadamard if the UV behavior of its two-point function mimics that of the Minkowski vacuum, or in real space if the coinciding point limit of the two-point function is mimics that of the Minkowski vacuum. And one can even express that concretely. So for X and Y being 2 points in the manifold that are sufficiently close so that they can be connected by a unique geodesic, we require that the two-point function their two-point function consists of two pieces. One piece that is exactly the Hadamard parametrics or a Hadamard parametrics, and a second piece that is smooth. And the Hadamard parametrics for the scalar field has this particular form here. Sorry, where U and V are smooth functions that are completely determined just from the local curvature and the equations of motion.
Christiane, may I ask a question? Extremely
Yes.
sorry to interrupt. How is the geodesic that connects the 2 points uniquely defined?
Can you say it again, please?
How is the geodesic that connects the 2 points uniquely defined? Why is it unique? What is the prescription that you use to identify it uniquely?
Well, basically, you identify it by being the shortest connection between the two, in the sense of the proper distance measure.
And you also restricted, so you restricted time.
I'm so sorry.
No, I am sorry. Bless you also. So you restrict to time like curves.
No, it can also be space-like. And you just have the different sign that you can still
Then you look at the
find
shortest.
the shortest connection.
Okay.
Basically, it becomes complicated. Like on a sphere, it becomes obviously complicated with opposing points because they can be connected by like all the
Yeah.
GG6. So
Okay, thank you.
things like that throw you off. Yeah. Okay, so yeah, these are smooth functions that are uniquely determined by the local geometry and the equation of motion of the spacetime. Sigma is the geodesic distance, squared geodesic distance. It's also called the Sinch word function. Mu is just some arbitrary scale that you put in. Yeah, and that's basically all the pieces here. And then again, you have this smooth piece, which again now contains all the information about your state, since we've required all Hadamard state to have this singularity structure. So that also the difference between two Hadamard states will then be something smooth. Or the 2-point function of two Hadamard states will be something smooth. And let me also tell you some important facts about Hadamard states. First of all, they have the nice property that if you have determined that the state is Hadamard in some neighborhood of a Cauchy surface, then it will be Hadamard throughout your whole space-time. You might also be worried that maybe we've done too much of a restriction, and once we restrict to Hadamard states, there are no states left. This is not the case. There indeed exist Hadamard states on any globally hyperbolic spacetime, which can be shown by a deformation argument. And the last point here, which is really important also for what I do, is that this Hadamard condition, namely that this 2-point function has this particular form, looks like it's kind of easy to deal with in proofs, but that's actually not the case. So a lot of the advances in recent years in quantum field theory on curved spacetime, and particularly the algebraic approach, are based on a result by Radzikovsky, which tells you that this Hadamard condition is in fact equivalent to a condition which can be formulated in the language of microlocal analysis. And this language and the powerful tools that it contains then really allow a lot of the proofs that have been done in recent years, also including this extension of the algebra in the first place. Okay. Are there any more questions on Hadamard states? Yeah, as Dan wrote in the chat, of course, this unique geodesic is only uniquely defined on geodesically normal neighborhoods. But in the end, we're, as I said, interested in the UV or coinciding point limit. So this is not too much of a restriction. Some people also make a difference between a local Hadamard property, which would be what I just showed you, and a global one where you also in addition demand that there are no additional weird singularities at space-like separation, but you can in fact also show that this microlocal property that we usually work with actually covers both. Okay, so then let me go on and let me introduce you to a little bit of what I'm currently working on and demonstrate you that, okay, now we've built this really abstract algebra. We now want to study a concrete problem, and we need a state for this concrete problem. What do we do? And how this is really not that easy. Okay, so the concrete problem that I'm looking at the moment is the Kerr-de Sitter spacetime. So the Kerr-de Sitter spacetime describes a rotating black hole in the presence of a positive cosmological constant. So we have 3 different horizons, as you can see here in the Penrose diagram, which was, I think, first constructed by Carter. for Kerr, we have an inner horizon of the black hole, we have an event horizon of the black hole, and we have a cosmological horizon. And this region 1 here would be where a would-be observer of the black hole would live. And the regions 1, 2, and 3, together with the horizons between them, can be shown, or that should be junctions, not over. Yeah, that should be caps instead of cups. But the junctions of these is a globally hyperbolic spacetime. So we will actually neglect this region 4 and ignore that it exists and only work up to the Cauchy horizon. And we will try to find a state that is Hadamard in these 3 regions so that we can, for example, study things like the stress energy tensor of this free scalar field near the Cauchy horizon, like in the example of the charged black hole. Okay, how do we construct the state? The idea behind the state that we're constructing is actually borrowing a little bit from the very classical approach to quantum field theory that is often taught in textbooks, that when you quantize your field, you just expand it in modes, in terms of modes, which are solutions to your equations of motion, particular modes with positive frequency, and then just declare the coefficients of this expansion to be creation and annihilation operators, and say, well, the vacuum is the state that annihilates all the annihilation operators. And we will actually use a similar idea. The difference on curved spacetime is that while on flat spacetime, there is like a unique time that you can choose, and in the sense, a unique sense of what a positive frequency is. This is not the case in a curved spacetime. There are different ways to determine what a positive frequency mode means. And so in this sense, picking a state a little bit in this example comes down to picking how you define positive frequency. And the idea of the Unruh state, well, he originally designed it for the Schwarzschild black hole, is that we choose the positive frequency by looking at the asymptotic behavior of our mode solutions near the past horizons, and then choose the modes that behave like free waves, basically with respect to the large U plus and large VC coordinates, which are basically the affine coordinates of the geodesics, which live on these horizons. And this is a choice one can make. One could also choose a different time-like coordinate to define positive frequency. But this is, as I said, the choice inspired by the Unruh state. Technically, how we implement this is we say that our 2-point function consists now of 2 parts, one for each of these horizons, where we plug our test functions first into the commutator function and then into some bidistribution. And this particular bidistribution now lives on the corresponding horizon. And it's basically just a delta distribution in the angular parts of the coordinates. And then the 1 over L minus L prime, where this L can be either this U plus or this VC. Okay, so this is how we define the state. Now, it's really not that trivial to show that this is actually a well-defined state, and even more non-trivial to show that it is a Hadamard state. Well, let me give you some hints how one would go about that. First of all, one has to show that this is in fact well-defined. The reason is that I said we plug our compactly supported functions first into the commutator function. So if we, for example, have a function which is compactly supported here, then the support of the commutator function acting on it will this be this whole region here plus something up here we don't care about. But in particular, it will be supported arbitrarily near I minus. So to really show that this all the integrals in the definition we just made are well defined, we will have to have some control about how solutions of the Klein-Gordon equation behave near this I minus. And luckily for us, in the case of the Kerr-de Sitter spacetime, there are some of these results available, which are by Hinz and Vargy, and we can use them to show that this definition is indeed well defined. The only property that we need, which is kind of free, is actually that this two-point function needs to be a bisolution of the Klein-Gordon equation. This is almost trivially satisfied because we first plug our test functions into the commutative functions. And since these are bisolutions, this already seals the deal on this part. We then need to show that this two-point function we have defined satisfies positivity. So if we plug in f and f bar, that we get some positive real number. And the way we do this is actually by a Fourier transform argument in this large U or large V coordinate. This is not as trivial as it sounds, because again, for this Fourier transform even to make sense, we have to control this behavior near I minus. But once we do that, after Fourier transforming, we can see quite easily that this positivity must be satisfied. And finally, we would like to check that our two-point function satisfies the commutator property. So if we subtract from omega2 of f and h, omega2 of h and f, so with the arguments interchanged, we should get I times the commutator function. And the way to see this is to use the form of the commutator function, which is just an integral over a Cauchy surface. And then basically from the idea do a limit Cauchy surface deformation, where we push such a Cauchy surface more and more to the past, to the point where it basically coincides with the two horizons, and then just show that the commutator function then really agrees with the antisymmetric part of our two-point function. And the final piece of the proof, which is probably the hardest and which definitely took me the longest, and I hope that I now have all the kinks smoothed out, is the proof of the Hadamard property. And the way to go about this is really throw a lot of micro-local analysis at it. And it becomes really, really technical. But it is doable. And once you've done that, you have yourself a state which is well-defined and Hadamard in these regions 1, 2, and 3. So you can then start and really study this free scalar field theory on this Kerr-de Sitter spacetime. And for example, see what happens to the stress energy tensor near the inner horizon of the black hole, and other observables you might be interested in. And maybe there are interesting results to come out of it, like in this case of the charged scalar field and the charged black hole, where we didn't expect it to stray so far from the naive particle picture. Who knows, maybe this might also happen for the rotating black hole. That's what we're looking into at the moment, and stay tuned. Okay, that's the end of my talk. Made it through more or less. Thanks for your attention, and I'm happy to take more questions.
Okay, thank you very much for this presentation. So then we'll continue to the discussion session. If KBO can stop the recording.